Hello and welcome everyone to Intro to Earth Engine. We're just getting started here. We are going to cover what Earth Engine is, why it is, what sort of pieces go into it, how it's all constructed, the motivation. This first hour is a bit more theory, and the second half is much more hands-on keyboards, typing, debugging. So if you're stoked for that piece, keep waiting. My name is Michael. I am a developer relations engineer on the geosustainability team, which includes Earth Engine and its a handful of sister products. I started on the team about 10 years ago. I was an intern, a software engineering intern, and I have been on this team for about a decade, helping build out a lot of the pieces, a lot of the back-end infrastructure, data processing, data ingestion, all the way through front-end tools, Earth Engine apps, which we'll cover in a bit. So I've touched many of the pieces, and now I work as a developer relations engineer, helping folks like you all and some of our commercial partners figure out exactly the best way to drive Earth Engine and what things we need to build next.
I'm Katie. I'm a software engineer on the Earth Engine team. I've been here for about a year. I was previously a software engineering intern also, but on Environmental Insights Explorer. And I've worked on a lot of our integrations with Google Cloud Platform, and I'm based here in San Francisco.
All right, we can get started. So this is our agenda for the day. I won't read it all to you, other than just to say that we're starting with the overview. We'll go into just some of the basic questions about Earth Engine and why it is what it is, how the computation works, and then what the future looks like. And then we'll have some time left over for Q&A. And again, this is the first bit. So this is our first hour. In the second hour, it's going to be all typing, higher pressure. Low pressure, but still higher pressure. All right. Let's do the overview. Welcome to the new folks. Fundamental question is like, why? Why is Earth Engine a thing? And we'll be sharing these slides, so if you're a note taker, or if you want a picture of me in front of it, it's a good time to do it. Why? So what motivates Earth Engine? Really, this is no surprise to anyone in this room that there are a lot of problems in the world. And in particular, this is kind of the motivating hypothesis for Earth Engine, that in order to really tackle these global challenges, people who are making decisions, people who are creating new knowledge, need to be able to ask questions and get answers from increasingly complicated and difficult to work with data sets. And in particular here, geospatial data sets. There are a lot of we call them decision makers throughout this space who need these tools. And so when we talk about the people who need to extract information and be able to make decisions, it encompasses all of these different archetypes, from folks in sort of policy to private and public sector, all the way through scientists, people making new knowledge, people working on the ground, to individuals and consumers who just want to make informed choices. So it's an incredibly broad term. There's a lot of categories represented here, and you saw many different names, examples on slides before, from Unilever or particular UN organizations, and I would like for you all to mentally slot yourselves into one of these groups as you think about the shape of Earth Engine. The problem, the difficulty here is that there's a lot of data coming in. The data streams don't take the exact names on these satellites as informative. This is really just to illustrate there are a lot of different satellite feeds. We'll talk in a bit about the specific kinds of satellite data that we have in the platform and some examples of common data sets. Just kind of be aware that there are a lot of data and there are terabytes of imagery and sensor information coming down every single day. In addition to the complexity of the data and managing those data, downloading, moving them around, storing them, replicating them, making them safe, backing them up, et cetera, we also have a computation problem. So in order to make sense of those data, even if you solve the problem of actually storing them and organizing them, making them useful and being able to ask those questions that you want to ask. How is forest cover changing in Ecuador? How have glaciers changed in Switzerland? How are the coastlines evolving off of Madagascar? Fill in the blanks. You need this computational heft to be able to make sense of these really large and complex data sets. So this is a quote that I think is really powerful and prescient from 2012, which is around when Earth Engine first became a publicly available product, that talks about this new paradigm which is required for remote sensing and understanding geospatial data. And in particular, focusing on collaboration, large amounts of data, huge amounts of computing resources, and then high-end visualization. We'll dig into high-end a bit, but just this flow of collaborating with these really massive and difficult to compute with data sets. So here is our basic problem. The idea here is that there exist many problem spaces where the solutions are blocked by access to tools, and in particular computing tools, IT tools, the ability to do scalable computation. And so this really is our motivation, why we exist, why this platform is why we have events like this. We want to make this not true. We want to ensure that these problems are not limited by something that Google has, honestly, an abundance of, compute and storage resources. So Jim Gray, who's a famous computer scientist, has this great quote about co-locating data and the machinery to interrogate the data. Really moving questions to data. And if you leave with nothing else today, the idea that you can bring your question to data is like the basic idea of Earth Engine. Everything that we've built, all the technical pieces that we'll talk about, are really structured around moving questions rather than moving data. And if that sounds like mysticism, we'll dig into it a bit more. But really, meditate on this for a second. This is a big idea. For broader context, this is Google's mission statement, and it has been for quite some time. Organizing the world's information and making it universally accessible and useful. If you see a Googler here, just tap him on the shoulder and you can probably get him to recite it word for word. This is essentially Earth Engine's mission as well. We just add the word geospatial in there. So we are organizing these information and making them accessible and useful. Our goals, and as I've been on the team for roughly a decade, our goals have not really changed. We want to build this really advanced platform. We want to integrate it into other Google products and services, and we want people to actually use it and have it drive solutions to exactly those kinds of problems that I highlighted a couple slides ago. Everybody on board so far? Y'all are a quiet group. Post-lunch. Okay, so that's the why. That's the motivation for why we built what we built. Here's the what. And we can roughly break it down into a couple of pillars. The first is that we have, you can just focus on the colored words if it's helpful, a large collection of scientific data and computational power to make sense of those data. So those things live together in the Google ecosystem. And then we have this Earth Engine API that makes those things available. And I have an experimental for this group illustration of this a little bit later. But really, these are the big pillars. We have data, we have compute, and then we have a way to combine those two and stitch them together and ask those questions. So I talked about 3 pillars. Here's a 4th. The data, the computation, the API, and then also we have our IDEs. And so an IDE is an integrated development environment. Really, it's just a fancy way of saying a place that you can write code and interact with the data products that you're creating, really formulate the questions that you're asking, do things like inspect pixel values, read dictionaries, and look at intermediate state, do debugging. We have a browser-based IDE, and that's really cool because it means that you don't need to maintain a desktop installation. You don't need to have a beefy supercomputer with a bunch of fancy hardware in it. I have done terabytes worth of processing over dozens of machines, maybe even hundreds of machines, from like a coffee shop on a laptop, because I am steering something that's happening remotely. And so these are sort of the ingredients that we mix together to get an Earth engine. We're just going to dig through each of these pillars. Stop if I go too quick, because I know we are tight on time, and I'm based in Switzerland. I'm pretty jet lagged, so I've had a lot of coffee. Start with the data. So we have many different kinds of data in Earth Engine. The real important number here is the 70 petabytes that we store. A petabyte is 1,000 terabytes or 1,000,000 gigabytes of data, and we have 70 of those, and it's growing super quickly. This slide is perpetually out of date because we grow by about 2 petabytes a month. The number of public data sets, you all can read that here. This really just speaks to the fact that we are trying to make good on our mission of bringing in these data to make them useful. And so when folks do processing, really each of these data sets is one that you don't need to worry about curating. You don't need to worry about handling the downloads and managing the FTP connections, et cetera, et cetera. These are data sets that you can reference just by name and ID, and we'll show some examples of that. To give a flavor of the different kinds of data sets, so I just like the circles on this slide, gives kind of a feel of the different types of data and the ways in which data can be represented. So there are some kinds of data which are just imagery, just optical imagery. There are some which are also optical imagery, but use different sensors and image the whole world every day, as opposed to little chunks continuously. Vector data sets, so these are things like country boundaries, geopolitical boundaries, river networks, road networks, things that you can represent as vectors, things that don't necessarily have pixels. Terrain and land cover, weather and climate data, just many different sort of shades of data. And an important thing to also add on this slide is the fact that you can integrate your own data into the platform. So if you have data that you can express as a shapefile, as a collection of geotiffs, you can bring those into Earth Engine and use them in the same way that you reference these data sets. Everything can live together and you can ask your questions to the corpus of data. They're yours, they're private until you choose to share them, but you can share them. Yes? The question is, are the data sets public from the beginning, or does Google acquire them and make them public? They are almost all entirely data that start public, and we are organizing them. So we are doing a bit of curation and librarian work to organize them, make them available, make them appear in a consistent format and live with other data in our system. But yes, they're mostly data that are public domain or licensed for like CC BY. The rough idea, if I can paint a picture for you of how different satellite data set availability works, is that you really get to choose 2 of any one of these 3 features. So you can have high revisit frequency, which is how often I look at the exact same point again. So if I'm interested in what the weather is for Sunnyvale, if I have a high revisit frequency, I can get that more often for Sunnyvale. Spatial resolution, that one's pretty straightforward. It's how fine I can identify the features on the ground. And then spatial coverage is how much of the world is covered. So sometimes I can get really high revisit frequency and really low spatial coverage. So it revisits just this point very frequently, but it isn't looking at the whole world, for example. And so roughly, there are, I haven't put any numbers on this slide, well, 2. There are no numbers here. This is just a rough tool for thinking about when you're working with data and you say, oh, this data set would be great if only it had more of another thing. Remember that you usually only get 2 of these. And we'll walk through some examples. So this is where the numbers start to appear. These are our major satellite collections. So these are missions that are flown usually by large government projects, research organizations in, for example, the US, the USGS, in Europe, ESA. There are many others, the Japanese Space Agency, often space agencies that fly these satellite missions and collect data and make them publicly available. So Landsat is, I believe, still our biggest collection overall. There are many different individual satellites and missions that have gone into Landsat. And they start from actually the 70s, and they provide varying resolution over time, obviously getting finer over time. Currently, they provide about 15 meters of data with a roughly 16-day revisit. And these numbers are numbers that will slowly go down as they launch more satellites, but that's roughly the idea. Sentinel-2 is an optical sensor from the European Space Agency, and it also has sort of similar performance characteristics there. This is just, again, to give you a kind of flavor of the kinds of data that you can expect, the kinds of resolution and revisit time that you can expect from various data sets. Digging into Landsat a bit, there are 8 different Landsats. See if you can spot which one's missing. That roughly have these different characteristics. And so you can see they go all the way back to the 70s, but the resolution in the 70s wasn't so great, or at least wasn't as great as what we have today. Okay, keep rolling. Sentinel-2, it's just a pretty picture. There are also some sources of high-resolution imagery. Most high-resolution imagery is commercial, and it is not available in Earth Engine. There are some kinds of data which you can purchase and put into Earth Engine, but broadly, the freely available data is not typically super high resolution like you'd see in Google Maps or Google Earth. Question? The question is, can you buy through Earth Engine some of these high resolution images? The answer is kinda. In particular with Planet, Planet has a data distribution mechanism, so you purchase through Planet, and you can get those data, access those data in your Earth Engine account, and we're real excited to figure out how to make A, that smoother, and B, make that happen with more sort of data distribution organizations. So yes, actively working on it. Question is, what's the resolution for Planet? I think it's 3 meters. Somebody keep me honest. Sean. I'll try to repeat all that. 50 centimeter, they have a 1 meter base map, and it got blurry towards the end. 3 meter, 2-week cloud-free mosaic products. That's Sean, everybody. Yes, so that gives you a rough idea. And again, these are typically limited in the spatial extent. So you don't get the whole world, but you get potentially high revisit time and high resolution there. Okay, cool. All right, so we also have a different flavor of data. It's called SAR, synthetic aperture radar, and it is different from optical imagery. So your phone on your camera is more of an optical sensor. It looks at just the light that is reflected, bounced off the surface ambiently. SAR is really cool. It's literally shooting radar down from a satellite and looking at the polarization that comes back. And to me, this sounds like science fiction, but no, it's a real thing. It's been flying since 2014. This is really interesting because it is not optical. You're not getting red, green, blue. You're getting back complex numbers for every pixel representing the polarization of the signal. It's complicated and it's different because you don't have sort of that interpretability. Your brain doesn't work like this. But it's really cool because those radar signals penetrate clouds. And so every image is cloud free. The price you pay is that it's not optical. Okay, so that's Sentinel-1. We can talk more about it. I'm going to go real quick through this slide just for the sake of time. There are many really interesting applications. I like to highlight this because it is just another cool sort of angle through which you can look at the world. Here are some ships. It's looking at the polarization of what comes back. So flat water polarizes the response differently from like the metal on the side of a ship. So we're looking at the port of Shanghai here, and Singapore on the left. Another cool one, areas with a lot of ice and a lot of rain are typically pretty rainy and pretty cloudy. So this is an incredibly clear picture of a like US state-sized chunk of ice floating into the ocean off of Antarctica. All right. There are, again, just many different kinds of data. Some are derived products. So these are products that have gone through some kind of classification, filtering, really providing some higher level classification or information about what's under the pixel. So you can get things like, is this snow or ice? Is this a forest? What land cover class is this? There are many different kinds of these data, digital elevation models, et cetera, et cetera. The Earth Engine data catalog is the place you should look to find out more about the different kinds of info that are in Earth Engine. All right, and we just have some razzle-dazzle slides here, talking about, again, just different data types. I'm a sucker for pixels and visualization, so this is what you get. Yeah, different terrain models. Again, mostly these free open data products. If you have access to higher resolution terrain products, you can, of course, bring them into the platform. Again, another animation that I really like. Sentinel-5 is cool. I can dig a little bit into this. This is just looking at air quality, so getting columnar measurements of carbon dioxide, nitrogen dioxide, just different gases throughout the atmospheric column. And this is really cool for providing information about pollution or about fires or anything that's dumping a bunch of new gases into the atmosphere. And again, here's some cool animations. All these data sets, I should mention, we download every day, all the time. We're getting new information basically as soon as the provider makes it available. So that is the key driver of latency from when the satellite actually takes an image to when it's available for you all, is just how long the provider takes to provide the image. We're constantly, terabytes per day pulling new data from different systems. All right, so that is all condensed into this little nugget of EE data catalog. There are many layers on top of the Earth Engine data catalog, and I'm going to try to go real quickly. We have this compute layer that I talked about, with the pictures of data centers and stuff. There are two different types of computation in Earth Engine. We have on-the-fly compute, and we have batch compute. This is like, give me something that's pretty quick, 5 minutes. Give me a map tile, give me a thumbnail image, give me a number from a dictionary. Batch computation, or we'll sometimes call it offline computation, is much more about run through 15 terabytes of data per map tile and dump out information into a different system. Google Drive, Google Cloud Storage, back into Earth Engine. That's where you can run computation for days rather than just the minutes that you have on the fly. On the fly is what you want to use for an interactive tool. So if you're building a web app, you're using the on-the-fly environment. If you're doing some real heavy computational work, head for the batch world. Okay, so that's a quick overview. As a question? The question is it CPU or GPU? It's all CPU. Yeah, everything is CPU. There's no reason that can't change. It's built on CPUs today. So we make this compute available via something underlying which hopefully you won't need to interact with too much early on, called the REST API. This is our lower level API application programming interface for accessing and manipulating these data objects and performing computation over them. The reason I bring this up, this is what powers our, well, it's a little more lower level, so you'll see that it's kind of grungy. If this doesn't make any sense, it's a little bit by design. This is a much lower level interface for interacting with Earth Engine than our client libraries. So our client libraries are built on top of the REST API, and this is where the JavaScript and the Python appear. The JavaScript and the Python are client libraries in Earth Engine. And those client libraries are open source. They are available on GitHub, PyPy, all those open source distribution platforms, Node or NPM. And you can download these, you can interact with these. These are what enable you to drive the REST API, which drives the computation, which can use data. So this is the expanding sphere that we're building. Okay, any questions so far? Cool. All right, and on top of everything, so the client libraries are the tools that you subsequently use to build user applications. And here, user applications is everything from the tools that we build, like the code editor or Earth Engine apps, to any third-party tools, like Global Forest Watch or Tracemark, or any of these tools that you're seeing being shown off that are powered by Earth Engine. This is kind of the level of interaction. This is where they show up in our grand map here. Okay? This is the first time I've shown this diagram. Usually I just gesture a lot. I'm finding this very helpful. My arms are less tired. Okay, so I talked about the higher level applications. This is the code editor. I'm sorry, this is super hard to see. No. Yes, all right. It's just difficult. I'll read it. It's a web-based environment for interacting with Earth Engine, for managing your scripts, your data, investigating data sets, and really constructing other interactive tools like Earth Engine apps. So this, I think about it like this is kind of the workbench that you'd use to drive your Earth Engine compute and interaction. This is, for me, the easiest lens into Earth Engine. And this lets you build things like Earth Engine apps, which are just simple standalone web pages powered by Earth Engine. They're basically, we'll go into it later, but they're basically this lower half of the screen, just the interactive pieces without any of the code or documentation or interactivity stuff that's built on top. Okay? And so these are Earth Engine apps, and that completes our grand ontology of how Earth Engine works and the different nested layers. You all are now experts in what Earth Engine is. Any questions? Super. Okay, so who uses it? Sorry, that was too fast. Who uses it? These are, we had to really, I could only get thumbnails for so many applications. These are some examples of data products. So these are products that people have built using the platform. This one is our first big one. This is a map of all the tree canopy cover in the world since 2000 and how it's changed over time. They update this data. This is the Hansen Lab at University of Maryland. Another nice example of a global data product powered by Earth Engine that, again, uses like petabytes of input information is identifying all of the surface water around the world over time, looking at the dynamics, how it changes. This is what Rebecca mentioned as being a tool used to power reporting for countries reporting on droughts, getting international aid, getting UN help for water management. This is a tool they use, and it was built in Earth Engine. And the last one here, I honestly really just like the picture, and I was very fortunate to be a co-author on this, measuring intertidal flats, so looking at the areas that are sometimes wet with the ocean and changing tides, and how those are really important reservoirs for biodiversity that are disappearing roughly at the rate of rainforest. So they're not great news, but important to be able to measure and quantify, and is the first step for actually having policy and structure around conversations. So these are data products. These are sort of the first layer. We also have applications like Forest Watch, which I think was mentioned a bunch earlier. This Offcast, which you all saw, predicting mosquito populations and mosquito presence, and things like Tracemark for doing sustainable sourcing of different materials. So these are kind of one level higher in the science and application space. These are all user visible and accessible tools. Just to paint another picture, here is a snippet of Google Scholar showing how many citations, how many papers referenced Earth Engine outside of just the abstract. You can see 2022, it kind of levels off because we're not done with the year yet, but we're going strong. This is, again, a cumulative graph. On the other side is the yearly count. This is one of the metrics that we pay a lot of attention to, is how many people are actually publishing and creating new knowledge, new scholarly endeavors powered by Earth Engine. Okay, and with that, I am done talking.
All right, so next we're going to talk about Earth Engine's computing infrastructure, talking about some of the technical details of how you use Earth Engine and how Earth Engine actually runs these computations. If this doesn't interest you, you can hop to a different session and my feelings won't be hurt. But let's jump right into some of the core concepts of the Earth Engine API. So objects are the building blocks of an Earth Engine script. A few key ones are up here to get you started. So we have geometries, which you can draw yourself with your mouse in the code editor on the map. And then one step above that, we have features, which is just a geometry with attributes. So if you know what a GeoJSON object is, it is exactly that. But if not, you can think of it as a row in a table where one of the columns is the geometry, and then you can have an arbitrary number of columns with other properties describing that geometry. Next, we have an image, which is kind of a feature plus pixels. So it's a stack of georeferenced bands where each band has its own resolution and projection, which is really helpful for working with multispectral data like Landsat, because not all of the data is available in the same resolution. And the image will have additional metadata that you can filter on, like a date and a bounding box. And finally, we have a collection, which is just a bag of any of these other object types. So you can have a bag of images, which is an image collection, a bag of features, which is a feature collection, and that's a really helpful object for grouping other objects together and doing things like filter operations and reductions on them.
No, I can't. Yes, I can. One quick interjection about bag is a really important word here. The more you can think about collections as bags rather than being ordered lists is a really powerful and useful way to think about them. You can impose order on them, but order is a really difficult thing to parallelize. So we're showing you a bit of the underlying computing infrastructure here and the limitations of it. Earth Engine's fast because it's in parallel. And the more you can think about things as being unordered, just a bag of elements, the more we are able to parallelize your workloads.
Yeah, that's a really good point, and leads into the functions because it allows you to do map operations on these bags, which is one of the core Earth Engine functions that we'll talk about more. There are also thousands of other functions in Earth Engine, machine learning functions, image transformation functions, feature transformations. All of these are in our API reference docs and more. But to go into some of the core ones, first we have band math. So this is kind of the algebra for how Earth Engine objects behave when you apply operations to them. So let's say here we're adding 2 Landsat images, which both have 6 bands. The way that we're going to do that operation is do it by pixel by band. So we're first going to look at the first band and add up each pixel and get an output band. So the output is still going to be a 6-band image. You can also tell Earth Engine to add a single band to a multi-band image. If you do that, we are going to assume that what you want to do here is add that single band to every band of that first image. So we're going to do something called promotion, where we replicate that first band 6 times or however many bands are in that first image, and then do a per band, per pixel addition like before. Next, we have the map function, which you apply to a collection image. This allows you to define a function once and map it over each element in the collection. You can use Earth Engine functions or write your own, so you can do things like compute the NDVI for every image in a collection. It's an end-to-end operation, so if you have n objects in your collection, you're going to still get n objects out. Some examples here are getting the area for each feature in a collection, getting the cloud cover for each image in an image collection, or getting a composite image for each month in the year. The way you would get a composite image is with a reducer, or a reduce function. A reduce function lets you aggregate everything in a collection. So it's kind of the converse of a map function because you're going to be applying it to every element in the collection all at once to aggregate it together into a single object or into a couple objects. So for instance, you could have a feature collection of a bunch of different geometries, and you could use a reduce function to get a single value of the summed area of all of those features. You could use it to get a median pixel composite for an image collection. If you don't know what a composite is, it's basically just the result of applying an aggregator to multiple images and combining them together. Training a classifier is also in itself a reduction because you're reducing a bunch of images into a single classifier. There are a lot of different reducers in Earth Engine. This slide is basically just to say that. We both have ways to reduce, so reducer functions that you apply on objects, such as an image.reduce function, and then we have actual reducers, which define how to do the reduction. So things like taking the mean versus the median, or taking a sum or a max, those are actual reducers that you plug into a reducer function. Any questions before I go through some of these reducer functions? All right, so the first reducer function we have is reduce bands, which you would apply on a multi-band image to reduce the bands into a single band. So what Earth Engine is going to do is look from top to bottom across all of the bands in this image per pixel, and in this case, we're going to use a sum reducer, so sum all of those values together to get an output band. We can do the same thing on an image collection. So here we have 3 images with 3 bands each, and we're going to output a single image, but also with 3 bands. And the way we'll do that is, again, go from top to bottom, but look at each band at a time. So first, only look at the red bands, and whichever pixels we intersect are going to go into our operation and get an output, and then do the same for green, same for blue. So it's okay that the images don't totally spatially align, and just some of the values won't have all of the images in it. We have reduced neighborhood, which lets you look at the pixels surrounding the pixel, and you can do things like statistical analysis on that grouping. We have reduced region, which is often called zonal statistics as well, and this lets you do things like get the mean NDVI for a park or a city or whatever geometry you have, which is super useful. It's by default done per band, so if we have a 5-band image and call reduce region on it, our output is a dictionary with a value for each band. You can tell it to do it across all bands as well. And then finally, we have reduce regions, which is the same thing, except you're working with a feature collection. So we're going to reduce over all of those different geometries, and our output is going to be a feature collection with a value for each feature band combo. Okay, yes, question? So the question was, when I say pixel, is the size of the pixel dependent on the image's resolution? Right. Yes. I believe so. I think Michael has a more confident answer.
Yeah, pixels are essentially the units for grids on the surface of the Earth. And so the tricky bit is that most people agree the Earth is round. We have a lot of trouble making the round Earth into grids of consistent squares. And so pixels are those squares, and we talk about different projections and different resolutions. Really, those are just different gridding structures for describing the surface of the Earth. So even within an image, it's not always the case that a pixel corresponds to the same physical area on the surface of the Earth, because you can have things like, a good example is the Mercator map. If you look at Google Maps and you look at Greenland, it's way bigger. Each pixel there is proportionally larger, smaller, so the whole image takes up, Greenland takes up more space than looking at something close to the equator. There's less distortion. Question?
Maybe a point of clarification, you might have an after zone. If I'm working with a 30-meter image, 30 meter pixels, 10-meter pixel image, much like you were promoting one band to many, I assume you're promoting pixel size.
Yes, the observation was that sometimes you want to work with different projections and resolutions, different grids, and what do we do in that case? How do we make that work together? Stay tuned. We've got good structure there.
All right, cool. So here, this is just a pointer to our API reference docs. So everything I just talked about and much, much more is in this documentation. The client library section and specifically JavaScript is what will be most relevant to this session. But yeah, it's linked here in the slide. Okay, so putting these core concepts together to how a typical user might use Earth Engine. First, they might get an image. They could get this image from the Earth Engine data catalog, or they could ingest it into Earth Engine themselves. Then they might want to apply an algorithm to that image. So this could be something like the NDVI, which is normalized difference vegetation index and is a measure of like the plantiness or the greenness of the image. More commonly, our users are working with image collections rather than a single image. So they would download a whole collection of images, like the Landsat 8 collection from the data catalog, and then filter down that collection to get just the images that are relevant to them. So they could filter by a specific time duration. Maybe they're only interested in the year 2016. You could filter by a region. Maybe you only want images in California. Or you can filter by metadata. So you can do things like filter out images that have clouds in it, which is really powerful. Next, they might map an algorithm over the collection. So they still might want to be getting NDVI, but they would plug that into a map function to get it for every image in the collection. And again, it's an end-to-end operation, so they're still going to have the same number of images after that map function. And then they might reduce the collection. So simplify that image collection into a single image by creating a composite. Maybe they're taking the median image so they can nicely display the composite on a map and then compute some aggregate statistics on it. So getting some tables and graphs and real numbers that they can use in a paper or a presentation. Okay, so now we're gonna get really technical for how Earth Engine actually executes computations behind the scenes. And this is a little bit for like how Earth Engine can work on so much data pretty efficiently. So when you're writing code in the code editor, you're writing JavaScript, but that code that you write is not what is run directly on Google servers. When you click run in the code editor, the Earth Engine client library is going to convert that JavaScript code into JSON objects, and those objects are what are sent to Google servers. And these objects represent the operations you need to get to some desired output. And these graphs can be really, really big. They can have tens of thousands of operations. And Earth Engine is going to evaluate these expressions in a lazy way, which means that it's going to delay the expression of each value until it's actually needed. So nothing gets processed until Earth Engine identifies what the thing you want to materialize is. So maybe that's a map that you're trying to visualize in the code editor with a map.addLayer call. Maybe it's a value that you're printing in the console. you need to have that like core thing to materialize for Earth Engine to actually run anything.
Just a note here, to call back earlier, we talked about moving questions to the data. And this is the mechanism by which your questions get to the data and to the computation. So you describe what you want to have happen. You, at the root here is the artifact that you're materializing, the output that you want. Maybe it's a number, maybe it's a thumbnail, maybe it's a set of images, maybe it's a dictionary. And all of these steps are the processing required to get there. And at the very end, these leaves are the raw data, the information that you have to load from Earth Engine. So when you pass this, when you send this to the server, this is a description of computation. This is saying, how do I get the answer from the data that you have on the Earth Engine servers? And so this is the mechanism by which we're delivering on the move your question to the data. This is how you do it.
Yeah, and this helps Earth Engine not compute anything that it doesn't need. So if you define a variable that like requires a really expensive computation, but you don't actually use that variable, we get to avoid actually running that computation. Okay, so to kind of make this point more, let's look at an example. So let's say our goal is to visualize a max NDVI composite of Landsat images in the year 2016. So if you were to do this using a traditional GIS software, what you would probably do is start with downloading the Landsat 8 data. And this has over 1 million images, so could take you a really long time to download. But once you have that data, you're going to want to filter it by date. So we're going to get just the images from the year 2016. Next, we want to get the NDVI for each image in this collection. So we're going to go through each of these images and compute the NDVI for each one and add that as a band to each image. Next, we're going to take the output from that and put it into a reducer to get a max NDVI composite. So going from this 15,000 image collection into a single image here. And then finally, we're going to do some reprojection and visualization to actually visualize what we want as a map. And probably also cropping it, because we're probably not going to visualize the whole world. We're just going to visualize some specific region.
If I had to summarize this strategy, it would be pushing. We're pushing data from one step to the next. And each time we're moving a lot of data into each subsequent step.
Yes, exactly. And yeah, the thing here is it's storing a lot of intermediate states. So like after each step, it's going to store something so that we can do the next operation on it. So if Earth Engine was attacking this expression, we're going to do it in basically the opposite way. So Earth Engine is going to start by identifying the artifact you want to materialize, which in this case is this map visualization. And then it's going to work backwards from there. So once it identifies this, it's going to next identify like what is the input needed to create this. So it needs a composite of max NDVI. And next it's going to find what is the input needed to create that. And keep going down and down until we actually get to the raw data. And by the time we hit the raw data, Earth Engine has built this computational graph, and it knows exactly what you're planning to do with the data. It knows exactly which data you're going to visualize. We know the region that you're trying to look at, and that way Earth Engine can download less data or fetch less data. It will only get what it needs. And then once it has the data, it's going to pass it back up the chain and actually execute the computations to create your map. Yeah.
Just a quick question. So from the user perspective, does the user have to do this too, or does the user normally start with the data filtering?
Yeah, that's a great question. So the question was from a user perspective, do you build your script like this, or do you build it the other way? And the answer is the other way. And in JavaScript, so like usually the first variable you define will be like your image collection, and then you're going to apply subsequent operations. But when Earth Engine converts it into an expression graph, then we kind of flip it all over when we actually run the computation.
The top step here, the visualizes map, again, that can be something like give me a number, give me a dictionary, give me a grid of pixels. The idea here is that we know we can exactly enumerate the output area. And so taking a thumbnail, for example, we know the grid of pixels and the projection that you're asking for. And so you can think about this as each pixel can figure out, based on this graph, what is the information that needs to be collected, and how do we reduce that back into the output. So you're completely output driven. And this is the secret sauce, because this splits very nicely. If each pixel knows how it's computed, you can spread those pixels out across a large number of machines. This is a spoiler.
Yeah, that is an excellent transition into the next section, which is about this like scattering and gathering over multiple machines. So in order to do this, we do something called tiling. So when we ingest images into Earth Engine, we cut them into pieces to make them easier to work with. And those pieces are tiles, which are just 256 by 256 pixel blocks. And we keep the image in its original projection and resolution. We just cut it into pieces and then save that. And then we're going to do some downsampling. So we're going to create a downsampled version of the image by doing some averaging or a different aggregator depending on the type of input, and do the downsampling again and again until we get the image that an image that fits into like just one tile. And we're going to build this pyramid of different versions of the image at different resolutions. So most of the time when you're working in Earth Engine, if you're like scrolling around in the code editor, we're serving you images somewhere in the middle of this pyramid, because it's a lot faster for us to serve you a downsampled image rather than the raw image. But if you need that original resolution, you can explicitly tell Earth Engine to not do any downsampling, and it will be a little slower, but it will work. Yes. Okay, so now for parallelization. During a computation, we have, let's say this is the image that you're trying to materialize in the code editor. This is also going to be split into tiles, and we're going to split those tiles onto multiple different machines. So we have 16 tiles here. We're going to spread that to 6 different machines, where each machine is only responsible for a single tile. And it's going to do that whole computational graph for the tile. And then at the end, we're going to gather the different tiles together to display you like a cohesive image. And one of the important things here is for the machine responsible for this tile, when it gets down to the bottom of the computational graph, and it's actually fetching the Landsat data, it only needs to read the Landsat images that intersect with this code editor tile. So here it's only going to fetch 4 Landsat images rather than fetching like thousands or hundreds of Landsat images, which makes everything just way quicker to compute. So in Earth Engine, we have...
Question?
Oh, yes, sorry.
About the tiling?
Yes.
If you do a computation that relies on the neighboring pixels, and then those neighboring pixels are in the other tile, do you compute each tile with a certain border of pixels around it, so that then when you stitch it, it's going to like take into account the neighboring tile?
Yes. The question is, when you're constructing an output pixel, sometimes you need to rely on information outside of the particular borders. A good example of this is when you do a convolution operation or a blurring, and you need information from a strip bordering the output. Yeah, each algorithm in Earth Engine defines how much space it needs from other images, and you will do recomputation. You'll use some of those overlaps when we're producing the outputs. We'll do some redundant computation because it's being computed separately. Yes, so the kind of short answer is you don't need to worry about the amount of you don't really need to think about that as you're doing the processing. We're handling the division, and that's kind of the magic here, is that you get to build this graph, and we figure out how to parallelize it and to make it efficient. That said, there are some applications which don't work well in Earth Engine, just ones that rely on pixel information from a very large number of pixels away. And so an example of this is something like hydrological flow, where my flood model, the value at San Diego depends on elevation from the flood basin or whatever. Those tend not to work well in Earth Engine because you need to move a lot of information far, like across a large number of pixels. That's not a good fit for our computational architecture.
Sorry, I'm a little confused about the tiling also. So you said that the tiling is to make things more efficient, so that you reduce the amount of pixels that you do. But here you're showing that there's 4 images in one tile, like overlapping. So I thought like tiles were smaller than images.
Yeah, that's a good question. There are multiple different types of tiles, and Michael, feel free to jump in, but here we're talking about tiles in the code editor for what we're displaying for you, but each of these Landsat images are also split into tiles which define how we do the downsampling on the image. Does that make sense?
If it's confusing, there's a message that you need to extract from this slide. Really, one is that we do all the reprojection on the fly. So based on the image that you request, this black square here, we will go and we'll figure out the input that needs to be fetched to construct that output. We'll fetch that, and then we'll do the reprojection, and we'll handle all of the input projections, and really you only need to think about the output projection that you've specified. And when you're looking at a map, it's intrinsic. Each of these squares has a pixel grid with a projection and a resolution. But if you are, for example, creating a thumbnail and you say, I want it in this funky geoid with all these different projection parameters at scale, you don't have to think about, oh, this uses 10-meter imagery, 30-meter imagery in 2 different projections. This goes back to the point earlier. Earth Engine will gather all of the inputs and reproject them into your output space, and that's where the computation happens. Maybe that's more confusing.
Yeah, the nice thing is Earth Engine is doing all of this reprojection for you, so you actually, as a user, don't need to understand how exactly we're doing it. Yeah, we can talk more. Okay, so one more slide before we can dive more into Q&A, but just to summarize, Earth Engine's lazy evaluation on these expression graphs combined with downsampling and parallelization on Google's computing infrastructure is really like what makes Earth Engine so powerful and able to run such huge amounts of data efficiently. Oh, sorry. We also have some more slides that Michael's going to give.
Let's blitz. Yeah, I think it's just this one.
Yeah.
Yeah, so we have a lot of this talks about our, where we started, our motivations. Also want to just point at where we're going. Really should have updated this because we're in H2 2022. Our big focus has been that second bullet that I pointed to way back, talking about our goals, integrating into other Google products and services. This has been a big theme for us over the past 3 years, and this is the Earth Engine appearing as a Google Cloud API, a Google Cloud tool, and integrating with other tools in Google Cloud. Things like Vertex AI, things like BigQuery, those are on our roadmap as really important integrations, and we think there's a lot of value in Earth Engine being able to be sort of fluently translated into those other computation environments. Yeah, so we launched Earth Engine as a generally available GA cloud product earlier this year, and now we're really focusing on the interop and on the scalability. So being able to use it in different ways throughout cloud, and also having those uses scale larger, deeper time series, more intense computation, heavier classification, you name it. And that's Q&A.
Yeah, we hit 2:15 literally on the exact second.
I'm based in Switzerland. They you all probably don't have any questions, right? Yeah. Okay. Yes.
When you do the downsampling and then, so we've run into situations where the tiles aren't available. Either there's cloud cover, and then, or there's really just a swath of no image. Is there a way that the Earth Engine's able to flag an error, or after doing all your computations, once you get, let's say for a region, so we use GeoJSON files, a region that's very specific, that it's just a black tile. Does that factor into the computation, that the final, whatever, median or average? Is there a way to capture that?
Yeah. For me, this is a question about filtering and how you do filtering and how we do filter propagation. And is it possible to reject regions early, or to, when you've done your computation and you see that there are no results available, the tools that I would reach for are filtering and masking. So masks in Earth Engine are this concept of a pixel that doesn't have a value or only has a partial value. We'll dig into that a bit when we make mosaics in the second half of this, when we start tapping on keys. But those are the very high level concepts. It's a bit of a deep question, but fundamentally what you want to do is you want to have a metric that says, hey, there's no data here, and then be able to filter out and exclude those particular polygons. Other questions? It's a fun microphone. Yeah.
Thank you. My question is about the data collection available in the Earth Engine, and particularly the vector data. Some of the times the vector data is either modified or renamed, or new data is uploaded, the old data is removed. Is there a place where we could know that what is the replacement or the modification into that data? And my question is coming from that I had script that I didn't use for a year or so, and when I used it again, that vector data was not there. It was removed, so I couldn't use it again.
Yeah, we care a lot about data integrity and reproducibility. That's a big theme for us, as you saw the graph of papers published, and that's our bread and butter. Our underlying ethos is really you should be able to reproduce and have results that continue to be valid. For vector data in particular, those data sets tend not to be changed. I would happily, if you have a particular example, I'd happily look at it. I know we do have a handful of data sets that are labeled current, and so those do change. And so if you want to pin your computation to a particular slice of data, I'm thinking right now about WDPA or some of these Tiger Roads data sets, you would not use the current. That just gives you the latest slice, but you can use a named and versioned pointer to those data. We try really, really hard not to delete anything, and not to change anything. I write a lot of software, and I feel that pain. I do not like when things change. So yeah, it's that's a big theme for us, and I'm happy to dig into that. We're over time. I will not let people leave. Yes. Sure. Fine. Okay. Yes. No, we'll take a quick break, right? Sure. Yeah. Sorry, we ate into your break. That's why you're here, right? Learn about Earth Engine. Yes. Please come back in 10 minutes, and we will grab some code.